I'm Matt Cederberg, Chief Strategy Officer at Coreform, and I'm really pleased to have Dr. Steve Owen from Sandia National Labs who will be presenting today's webinar. This is the first of two webinars that Dr. Owen will be sharing with us about the new machine learning capabilities. So the focus of today's webinar will be on defeaturing, and we will just briefly first introduce Coreform Cubit if you're not familiar with that software. Then Dr. Owen will talk about what defeaturing is and why it's a valuable part of preparing models for simulation. And then for the bulk of the webinar, he will be demonstrating how to defeature a part in Cubit first without machine learning to give context, and then introducing the new machine learning defeaturing tools. And just a reminder, the second webinar on machine learning in Coreform Cubit will be presented next week, and that will be focused on part classification and reduction. So just to introduce Dr. Owen a little bit more, Dr. Steve Owen has been developing Cubit for over 3 decades. So he's got a lot of experience. A lot of the meshing and geometry algorithms in Cubit came from Steve. And lately he's been focusing particularly on the integration of machine learning methods into this design to simulation process. So again, I'll just introduce Cubit. So Coreform Cubit is the commercial software used for advanced meshing for challenging simulations. This is based on the Cubit software developed at Sandia National Laboratory, which is where Steve does his work. And Cubit has a lot of functionalities that are very helpful for preparing models for simulation. Some of the top ones that people use Cubit for, the top reasons, one is it has very good ways to defeature and prepare models and partition them for simulation. Its hex meshing capabilities are best in class, and its integration with Python for scripting is used often for automated workflows. And today, Steve will be introducing the machine learning capabilities. So this webinar is being recorded. Throughout the webinar, Steve's open to questions coming in, and he's happy to address them throughout the webinar. So just go ahead and type them in, and we'll insert them and either answer them or ask them to Steve directly as appropriate throughout the webinar. And with that, I'll turn the time over to Steve.
All right, thanks. Let's see if we can share the screen here. Thanks, Matt, I appreciate that. So what I'm gonna do, I've taken this material from a series of lectures that I've prepared for our internal analysts at Sandia. This is fairly recently developed, since a lot of this capability is pretty new. But so what I wanted to do was kind of give you a framework for defeaturing within Cubit. So you may be aware that sort of the scope of Cubit is to, in general, you would start with a solid model that has been created in some commercial package or whatever your favorite CAD tool is. And the ultimate result is that you want to be able to generate a mesh, whether that's a hex mesh or a tet mesh, triangle mesh, quad mesh. And there's a series, I've represented this as sort of a linear process. Often it's sort of trial and error, trying to figure out how to get to that step 9 there. One of those processes is to simplify the geometry. So why do we simplify the geometry? There's a number of different reasons for that. So defeaturing is essentially simplifying the geometry. So if I was to start with the initial CAD model, and in the case for tet meshes, if I was simply to hit the mesh button, you might get the resulting mesh on the lower left here. And in many cases, there are just lots of little features that have been integrated into the design solid model. For whatever reason, it may be for manufacturing, it may be just for visualization, but in a lot of times these things are really not relevant to the end analysis, and in fact can distract from it. So in this case, with about 400,000 tets, it may be the difference between running, an analysis for a week versus a few hours if it's a complex model. So typically an analyst will take a look at that model, kind of figure out what's important, what isn't, and remove those features. And so in this case, as you're going from left to right here, we've removed a lot of that engraving there, some of the holes, some of the chamfers. And now when we hit the mesh button, we get about 32,000 TETs, and saving an order of magnitude. So this is pretty significant. So how do we go about doing that? And so what I'm going to do is kind of show you really 3 different approaches to it. The first is kind of a graphical user interface, sort of real hands-on visual type of defeaturing. The second is sort of guided by geometric reasoning. So it doesn't involve machine learning, but it's just sort of internal geometric algorithms that sort of point to places where we think there may be some issues, and the user still has to sort of decide, is this important, is this not, and they can remove those issues. The third one is where we will jump into machine learning. So obviously machine learning is why we're here. We want to learn about machine learning, but I think it's important to sort of put that in context, that we're not just jumping in and saying, okay, let's make machine learning the most important thing in Qubit and it's all machine learning. It's really not. It's a small portion of it now, and it's able to sort of guide the user now to a place where they hopefully want to be. So let's start with this sort of graphical user interface approach. So if you've used the Qubit GUI before, once you bring something in, as you click around on the object and right click on surfaces, in this case, you will be presented with a series of options, and these options are actually customized or customized for the context that it is. So for example, if you select something that looks like a hole, you will be presented with this select hole. So if I selected a single surface and then I did select hole, it would select the entire hole. So if there was a bottom surface or the hole was comprised of multiple surfaces, it would select all of them all at once. Other things like select similar. If I select something that has similar surfaces throughout the object, selecting similar will allow me to select them all with a single mouse click. Selecting blend chains. So a blend is basically often known as fillets. It has a radius and it sort of blends between, usually they're at 90-degree angles, and you're blending between those. And often that's not really relevant to the analysis and can add additional degrees of freedom to your solution. So sometimes it's good to remove those as well. So let me give you a quick demo of how you might use some of these. So I'm going to go ahead and I'm going to go ahead and import a model. So I've recently imported, so I'm going to use this recent imports thing up here on the left. And then I'm going to use this model here that's called ANC 101. So this is sort of a simple standard model that we use for training. Rotate it around, just looking at it. So just sort of visually looking at things. If I have some knowledge of this part and what it's used for, I could say, well, I want to use this for hex meshing, for example. And I know that hex meshing, I can't have a lot of extra things on it. So I'm going to sort of do some brute force, just go through and decide, okay, what do I want? What don't I want? So let's start with some things like, I'm going to make sure that I have my surface selector on up here on the top. And then I'm going to select a fillet, for example. And if I right click now, if I go all the way down to the bottom here, you'll see this little remove option here. And you'll see that anytime you have a surface. So if I do that, you'll see that it immediately gets rid of that. I can do that over here as well. And in fact, I can multiple select. So if I go through here, I'm going to hold down, I'm going to max, so I'm using the command key. So I can select multiple surfaces like that. If I right click and then remove, here it gets rid of all those. So I'm going to quickly go through and do a bunch of things here. So for example, here's a chamfer. I'm going to remove it. Here's a surface, or I'm sorry, a hole. So notice that I've just selected the cylinder. If I right click on that now, it says select hole. Okay, so now it's selected all of the surfaces, in this case, just 2. But now I not only want to remove just that surface, but I want to remove all of those surfaces that are similar to it. So if I right click now and say select similar surfaces, it gives me all of those automatically. I can right click and then do remove on those. Okay, so I'm going to go through and do some of these real quick. So here's another example. I can do select whole, select similar, and I think there's like 4 of those. I do a remove. Okay, so some of these are also kind of interesting. So this is what's called a cavity. So if I select one of those, I also want to be able to select all of those surfaces at the side here. So if what'll show up here now is this select cavity option. So selecting cavity will automatically select those for me. And then I can right click and do a remove, and that gets rid of that. Same with this one here. I'm going to do select cavity and remove. Okay, let's go through here. I'm going to do this is a hole. I'm going to remove it. Here's a cavity, and I'm going to remove it. Let's see if we can find some other ones. This one's kind of interesting because it's sort of 2 cavities. If I select this one and then do select cavity, didn't quite select everything I wanted. So I'm going to hold down the command key again, select another one, and then do select cavity. Now it's selected all of these that I want to get rid of. But these guys over here, they are similar to it. So if I want to remove those at the same time, I could right click and do select similar and then do a remove. So I've got them all removed at the same time. So let's look at where we are. There's a few more things I want to do just because I know where I'm headed here. I want to get rid of. So if I do select whole here, this will get rid of just this region here. I'm going to do a remove, and then finally this stuff over here. So let's get this one, select whole, holding down the command key again, this one, and select whole. So if I remove that, so I should tell you that remove will not always work, okay? Because it may wind up with a case where it doesn't make sense to remove it. So let's say, for example, I wanted to, if I say I've selected this surface over here, I say remove, it'll give you an error because it doesn't know how to close that off. It's only cases where geometrically it can extend those surfaces and then remove them. Okay, so why did I do it like this? Basically because I wanted to be able to hex mesh this thing, and it turns out that I should be able to mesh it just with mesh volume all. Okay, so if I was really using this, I would probably go in and set up some sizes, make sure that it was, everything was sort of where I wanted it to go. But in this case, doing that defeaturing allowed me to get to a point where I could actually do a hex mesh. Okay, so I'm going to jump to another mechanism for doing defeaturing, and I'm going to use this same model, and this ANC 101. So we're back to where we started here, and I'm going to use our power tools. So when Cubit comes up by default, you'll see this command panel that's sitting here, and this is where you can access a lot of your, well, really all of the commands in Cubit. There are a series of tools called the power tools. By clicking over on the right-hand side, the second one here, in fact, you can move that. So if you've got a lot of screen real estate, you can move it around if you want. And I'm going to double click to make sure it's full screen. And what it allows me to do, so there's multiple different tabs up here. Okay, and these are different power tools for different purposes. The first one is our wizard tool. The second one is what I'm going to focus on, and that's called the geometry power tool, or the geometry diagnostics power tool. So once I'm here, you should see this big empty panel here. And the first thing you want to do here is do this options panel. And what this does, so this list here tells me all of the different geometric diagnostics that Cubit is able to do. So basically, it does some internal calculations and figures out that, oh, I have a small feature, for example, or I have a bad angle. And so this just tells you which of those diagnostics you would like to perform. I've selected pretty much all of them. There's this newer thing called beams and shells that I'm not going to use right now. But basically, you can do them all if you want. In practice, however, if you've got a very large model, you'll usually want to focus sort of one at a time. So figure out, let's find all my small surfaces. Now let's find all my bad angles and sort of deal with one of those at a time. Now up here on the top, there's some different controls here. We're going to talk about machine learning here in a moment. I'm not going to do anything with that right now, but there are these threshold values, and this is how it basically threshold values that decide whether or not a diagnostic passes or not. So for example, a curve length, it tells me if I'm looking for small curves, for example, what's the what do I mean by small? What's the length that I mean by small? So you can actually enter a value here if I wanted. So if I said 1.0, it would look for any curves that were smaller than 1.0. Now that's easy to do. I could, however, usually I don't know what sizes I'm looking for. So if I do an auto size, it does an internal calculation, figures out, okay, here's a heuristic. Is this what you want? And then you can go from there and decide whether or not to change those. I should mention as well, if you already have a size that's set on here, these heuristics will key off of your size. So I'm going to do this from the command line. So if you use the command line, I can set a target element size from the command line. And so that's probably worth another webinar on that, but I'm just going to do volume all size, say 1.0. Okay. If I do size 1.0, that automatically sets everything to 1. And now when I do auto size, it keys off of that. So you can see the curve length, it's really just a quarter of the element sizes. So basically it's saying anything smaller than edge length 0.25, I'm going to key, flag you and tell you that there's a small edge length. So there's other things like the thickness of a chamfer or the blend radius. So if I can set that back to the default, default just by saying that. I guess that's not, I can do reset volume all. Okay, and that will get rid of all of those. And so now when I do an auto size, it goes back to the qubit selected size. Okay, so now that we know that, let's click on done. These are all of the diagnostics I'm going to perform. And now if I click on this analyze button here up at the right here, we will see a bunch of these diagnostics that appear. So these are basically lists. And so these are in the form of the lists that we selected. So for example, small features, it gives me a list of curves that are small. Here it gives me a list of angles that are small, and some traits. So things like, where are my blend chains? Where are my cavities? Things like that. Okay, so lots of things here. And so it's kind of like I said, if you have a complex model, you're going to have way too much information. So focus on one thing at a time, but just so that we can see it. Okay, so let's do, just because I want to demo something here, I'm going to do this. I'm going to right click here on something. So here I'm looking at small surfaces. I want surface 94. If I right click here and then I do zoom to, you can see that, there's a really small surface right here. You can see if I zoom into it. I can also do a right click. If I can't quite see it, I can do this locate and see it by itself. And in fact, you can do things like draw with neighbors. So it will focus just, if you have a very complex model, it'll just draw the surfaces that are nearby it. Okay. And to redo that, I'm just going to do a display here. And that puts everything back. And by the way, you can also do this thing here and say refresh display to get it back the way it was. Okay, so you can see that there's an issue here. So what do I do with that? Okay, so there's some different things that you can do. One is if I right click on it, I can, so you will find a series of operations that you could do with it. So if I click on this remove surface, Yeah, let's see if that works. So I think I've got my power tool there. There we go. Yeah, so what happened was it automatically went on the command panel over to the remove surface. So I could actually just hit preview and apply. So if the preview, notice that it comes in and shows you where that's going to be removed. And I can hit apply here as well. Okay, so now that's actually performed it. And you'll see that reflected immediately up here. So surface 94, it says that, oh, you've been deleted. But at the same time, it's also deleted some small curves. If I want to clean that up, I can say analyze. And now it shows me, oh, my small surfaces, you only have one small surface now. So let's go to Zoom 2. We'll find that.
Steve, there's a question that just came in.
Yeah.
So when you are removing these features, can you recover them later?
Later, as in immediately, if you've accidentally done it, then you can do the undo. Okay. And you can do undo as many times as you want. So that's one way to recover it. However, unlike what we call virtual geometry, which is just sort of a temporary sort of combination of surfaces, when you do a remove, that's what we call real geometry. So it actually modifies the underlying CAD geometry. So at that point, unless you have undo enabled, that's it. That's how you've modified your geometry. So it's usually a good practice to make sure if you're at a point that where you can't get back via undo and you want to get your model in a state that you want to get back to at some point, save it. Make sure you either got a SAT file saved or a CUB file saved. Does that make sense?
Yeah, and then just one other question. Does this machine learning work with all kinds of geometry or only the ACES geometries?
Okay, so first of all, we're not using machine learning just yet. However, what I'm demonstrating right now, it will work with ACES geometry. Will really any geometry that you bring in, with the exception of mesh-based geometry. Mesh-based geometry does not have quite the capability. So if you have a chamfer that is defined as a set of triangles, typically you're not going to be able to remove that. I'm not sure if that was your question, but
yeah, I think that's good. Yeah, thanks. Okay, you can proceed.
All right. Okay. So let's take a look at this Surface 95 again here. So I do have this little button called Show Solutions right here. If I click on Show Solutions, another window pops up here. And now here is a series of solutions that were generated automatically for me. It happens that the first one is this Remove Surface. Okay, that's the one I want. But there are some alternatives. So maybe I don't want to use that remove surface. And there's a few others like composite. So I may want to composite the two neighboring surfaces together. I may want to do what's called a rebuild topology. So multiple different options there. But I'm going to use this remove surface. Okay, so as I click through these, it gives me a preview. And then if I right click now, it gives me the option to execute. Or I can simply just double click and say, that's the one I want, and it will execute it. So let's do another example here. I'm doing an analyze. I'm going to go to vertex 95. It says I've got a bad angle there. I'm going to zoom to it. Okay, and let's go over here just so that I can see it. I'm going to do locate. Okay, so this is this vertex 95. If I was to mesh that right now, you may wind up with an element that has a really sharp angle. So typically you may want to get rid of those. And so what it shows me here, there is a series of sort of canned solutions that it allows me to do. And as I click through these, it will give me sort of a preview of what it will look like. Okay, so looking at the one that I want, let's say, okay, I like that one. If I double click on it now, it should modify my geometry and we're ready to go. Okay, analyzing again. And then I'm going to do one more over here. I think I like that one. So let's do that. Okay, so that's just a flavor of things you can do. There's a few other things. So traits, for example, let's look at chamfer chains. If I do look at that and I zoom to that, Here, let's refresh my display here. Zoom to chapter chain. Oh, it's interesting. It's only displaying that. Oh, I think I needed to do, well, okay, there it is. There it is. Remove surface 10. And let's double click that. Grabs that. Okay, so that's basically what I wanted to demonstrate. So there's various things that you can grab and execute and use either the command panel or you can use this solutions window. Okay, so what about this machine learning stuff? So lots of cool stuff that you can do just with this sort of geometric reasoning approach. And so let's look at this little button here. I'm going to reset this here just so that we can do another demo here. And I'm going to go File, Recent Import, this guy right here. Okay, if I do Options now, so I promised you that I would show you this load ML models. Okay, so what happens with machine learning? It basically has generated lots of training data. So it's seen lots of different CAD models, and it has a pretty good sense of under what circumstances will a mesh work for a particular CAD model. So what we'd like to do is to be able to predict the outcome of a meshing operation without actually meshing. So for example, I'd really like to see the places on this model where I can expect to have problems with my meshing. So when I say meshing, we're going to focus on TET meshing right now. The machine learning that we have right now is specifically for predicting TET meshing quality outcomes. So there's a couple things that machine learning will do. Number one, it'll find the most problematic features in your CAD model. So that is, tell me all the curves, or tell me all the surfaces, or tell me all the vertices where it will predict that there could be a potential issue with my meshing. What do I mean by potential issue? That would mean predict the mesh quality. So I'd like to be able to predict what the scale Jacobian would be without actually meshing. I'd like to predict what the in radius is. So scale Jacobian is basically a metric that says how good are the angles of my finite element mesh. In radius is a measure that says if I have a target element size of say 1 and I have a element that has 1, that's a perfect element in terms of in radius. However, if I have a size of 0.1, it will give you some measure that's much smaller than that because it's sort of a measure of how closely am I matching my target element size. Why am I interested in that? Mostly because if you have really small elements, that can really drive your simulation, the times of your simulation. So being able to detect places where small elements will occur is pretty important. Deviation is another one, and that's basically how well does my mesh fit the curvature of my geometry. So it's going to be able to predict all of those. Okay, not only do I want to predict that, I want to be able to predict, give me some, what do I do with it now? Okay, so I've got a bad element. How do I improve it? Okay, so the machine learning is able to say, okay, at this location, I think you should do a remove surface operation. If you do a remove surface operation, then I can predict that you're going to have a scaled Jacobian of a certain number. Okay, so what are those operations? We've developed models for about a dozen different of qubits operations, CAD operations. So for example, the remove surface is the pretty basic one, but others like composite, blunt tangency, and this kind of shows you little images of before and after. So how do we go about doing that? Let me go back to my little demo here. And if I now do this load ML model, what it will do, you might see some debug stuff going on here. We need to get rid of that. But basically it says, oh, I'm going to load what we call regression models. These are our machine learning models. And what will happen is you will suddenly get a bunch of new diagnostics. So notice without machine learning, I just have these. If I do load machine learning, and I just did it again, you'll get a bunch more. So I'm going to do select none, so nothing is selected. And I'm going to do collapse all, just so you can kind of see what's the main categories. So the ones that I'm interested in are this TET-mesh poor quality metric. So I'm going to select that right here. You'll notice that this part classification and surface classification also appeared. We're going to ignore that for now. And so stay tuned for next week, and we'll talk about those diagnostics as well. So we're going to just focus on predicting mesh quality outcomes. This also is dependent on a size. So we're going to use this auto size as well, and we're going to use the sizes that it gives me. But it also gives me some additional thresholds. So in this case, so for example, scaled Jacobian limit, it's going to find places on my model where it predicts that a scaled Jacobian will be less than 0.2. So if I'm really interested in, I can change that to a 0.1, 0.2, whatever that value is, it will only predict those that are less than that. Okay, so let's go ahead and try this. So I do an analyze now. You notice that our list has changed. If I expand this, it gave me two lists. Okay, the deviation, it didn't find any issues with the deviation, but it did find some places where it predicts that scaled Jacobian will be less than 0.2, and it finds the in radius or the scaled in radius less than 0.1, and these are the places that it found. So if I zoom to this, I'm going to right click and then do a zoom to. Okay, I know that, yeah, okay, so we've seen that before, okay? But rather than just sort of some geometric reasoning that said you might have an issue here, we have some pretty specific information. It says, if you mesh this right now, I'm going to predict that your scaled Jacobian is 0.17. So that may be okay. So 0.17 is actually not terrible. So you could probably use that. However, if I look at this one, this surface is also in the poor in radius. It says that the size relative to the target edge length is this 0.003. So it's really small. So it's probably a good idea that we get rid of this thing. So we can attack it from either of those diagnostics. And it now gives me this set of solutions. Okay, similar solutions we saw before, but some extra information here now. It now gives me, for this particular operation, it gives me a prediction of what the mesh quality outcome will be. So, for example, if I was to do this, I'm clicking on Remove Surface 94, shows me the preview like it did before. Now it says I'm going to predict that if I mesh this now with this surface removed, you're going to get an in radius ratio of 0.225. 0.4225, excuse me. So I'm going to double click on it, and then it should be gone. So you'll see that same thing happened here. It got rid of that. If I analyze that again, it shows me fewer things on my list. Same type of thing here. Okay, so you can see it's the same approach that we used before for the power tool, but rather than sort of doing it based on, is this a small surface, it's giving us some information about here's what I predict to be your meshing outcome. Okay, so let's do the same thing here. Let's do a remove surface, and then the vertex 94. So this is actually not terrible here, 0.197. I wouldn't do anything, but just for demo purposes, we should see this same guy right here. Okay, so now we can see the same options here, but now it sort of lists them based on priority here. So I can still choose anything that I want. And in fact, these two, you'll notice that they are identical in terms of the outcome. So you, as the analyst, still has to sort of decide which one is better. And in fact, you may want to choose one that's lower quality, but it's still within a range that is usable. So let's go ahead and just grab that. Okay, and if we analyze, we should have just one more. Okay, and then we can do this guy right here. I think actually, yeah, let's grab that. Okay. Okay, so that's the basic approach here. Let me do one more here before I wrap up here, just so that you're convinced that we do more than just this ANC 101 model. Okay, so here's our, and I'm going to double click and put that back. Okay, so here's our little car model here. So you can combine the approaches. So you can go in and remove things are that may not be what you want. So for example, hey, I know this isn't what I want. I can just go ahead and do a remove right now. There's this model I know has a bunch of things like some imprints on it. So I'm not sure where they came from. So these little curves that are sitting right here, we can get rid of those. And that's what's called a regularize operation. So I can say regularize volume 1, and that gets rid of sort of unnecessary curves, sort of redundant curves in the model. Okay, and that's usually sort of good practice to use this regularize operation. Okay, so now that I've perhaps done as much as I can, you may have a really complex model that has 100 surfaces or 1,000 surfaces in it. How do I go through each of those 1,000 surfaces and figure out where the issues are? So that's where machine learning and the power tools are really useful. Okay, so I need to get to my power tool here. Okay, let me move that over here. Okay, so let's do options here. A couple things here. So we've already got the models loaded, so we don't only have to do that once. However, you do need to set it up for sizing. So sizing is based on the model itself, and that may change. And again, we're just going to focus on TETMesh poor quality metrics. And if I do an analyze here, okay, in this case, we had 14 places with a poor scaled Jacobian and 16 places that had a poor in radius. So let's start looking at some of these. Okay, so we've got, it says it predicts that there's a bad scaled Jacobian here. So just so that we can convince ourselves here that we're actually doing something that makes sense, I'm going to do volume all size 1, and then volume all scheme TETMesh. So I'm going to go ahead and just mesh it like this. Okay, so we're going through using the Cubit TETMesher. It takes a minute, and you'll notice that, hey, there's a bunch of places here where it's really small, but let's actually measure the mesh quality. So if we do, I'm going to use command line quality volume all. I'm going to use a scaled Jacobian, and I'm going to draw the mesh. Okay, so now it shows me, hey, you've got a bunch of places that are bad. So if I look at this, zoom around, oh, look, there's these things are red. That means that I would get a bad quality mesh. Maybe these guys up here. Okay, it shows me that there's something that may be an issue here. So let's see if our machine learning actually finds those things. So I'm going to say delete mesh and start from scratch here again. Okay, and let's go to this guy here, and I'm going to do the auto size again, because I actually changed the size right here to 1. I'm going to do an analyze. Okay, so let's look at that vertex 9 and see what it found here, which is the worst one. If I zoom to this guy now, let's zoom out a little bit and kind of see. So notice that it zoomed right in without actually meshing. It found the place where it's going to be bad, and it says you're going to have a metric of about 0.05 if you don't do something here. Okay, so it shows me the best thing to do here is this collapse angle operation. Okay, and so I can go ahead and double click there, and it modifies it. And a collapse angle actually does some virtual geometry and combines some surfaces together. So let's go over here. Okay, so it's finding some of the same things over here as well. So let's do this collapse angle as well. Okay, so let's look at another one. Okay, so you notice I'm starting to find some of the same things as I go through, and you'll often find that in a single model you'll find a bunch of things that are similar. So you can indeed select multiple things at once. If you're satisfied with the top solution that it selects, if you go in here and say right click all the way down at the bottom here, it says execute 2 machine learning recommended solutions. So if I had 10 things selected, it would execute each of those 10 operations and choose the highest operations that it recommends. Okay, so it would go ahead and do that. And let's see if it did that. I think, so some of those, it may have, so it looks like they may have failed. So that was probably not a good demo to do, but let me see if I can find another one here. Here, let's do this one here. Zoom to, that doesn't guarantee that some of these will actually work. I think this one was the one I wanted to show you. Yeah, this one right here. So if I do a remove surface right here, it shows me that this will get rid of this guy here. This one is actually the same as well. Okay, both of these on both sides. So I could, let's see if it'll work on both of those. Right click and then execute 2 recommended solutions. Okay, so it did both of those. Okay, so at this point, I think I've sort of beaten this in. So if there's any additional questions, let me know. And we got about 15 minutes if we want to have a discussion.
Yeah, Steve, thank you so much. And I neglected to mention at the start, the training material that you're referencing is available at the Sandia website and the Coreform website. This is the material that you're the main author of, and it's just, I really appreciate learning from it myself. So there are a few other questions that have come in. So does the machine learning require internet connection, or is it an offline feature?
It is offline, yeah, there's no internet required. So what happens, when you say load machine learning models, that is actually packaged with Cubit now. You notice that your distribution is a little bit bigger. If you were to compare pre-machine learning to what we have now. So that's really the additional training data that it includes. At some point, I can imagine that we will wind up with so much training data that it may overwhelm our distribution. At this point, it's not too bad, and we may need to have an additional download for that. But at this point, it's included in your distribution, no additional internet connection required.
Great. Okay, another question. This is impressive. Thank you. When can we anticipate the integration of this feature with hex meshing?
Hex meshing is an interesting problem and actually much more complicated. So the basis for the training data that we're able to do with this is that we can quickly do a tet mesh on almost any object or CAD model that we bring into Cubit. And so there's pretty small percentage that would fail. So we can quickly do a tet mesh and figure out, okay, what's the outcome from any particular CAD model. Figure out, okay, at this point, there's a poor scale Jacobian based on an automatically generated tet mesh. However, as you may know, an automatically generated hex mesh is not so easy to do. So what we would need to do is, it would be a much more manual effort to be able to generate enough training data. So this example for this model, for example, would take a little bit of time to figure out how to decompose it and generate the hex mesh. Once you have the hex mesh, then you could establish some training data. And it's not to say that couldn't be done, but it's at this point, it was, in terms of a proof of concept, it was much easier to generate information for tet meshes. Now, I'm going to give you more information than you probably need to know, however. So what about machine learning to actually do the decompositions for you? That would be great. And in fact, that's a research project we're currently working on as well. So being able to say, okay, which web cuts should I do and in what order? So that's a pretty complicated problem to solve. And there's some research going on right now to do that.
Well, that sounds really interesting. Thanks. Another question, can you use the machine learning to train and recognize new parts?
Yeah, it's actually a good question. So right now you are limited to just the training data that is provided with the distribution. However, again, we're working on some capabilities to train on some new models. So if you have a new model, you want to be able to add additional training data. That's sort of underway. It's not in the distribution right now. On the other hand, what we will demonstrate in next week is machine learning for classification. So where basically you're able to choose or categorize the different parts in an assembly as a bolt or as a gear, etc. You are able to provide additional training data for that, and you can do that right now, and we'll demonstrate how to do that. So the answer to your question is yes and no, not with the TET meshing machine learning. However, I will demonstrate how you can do it, add additional training data for classification next week.
Great. Steve, thank you again so much for taking the time to, first of all, create this new feature and then write the training material, and then also take some time to share this with the Coreform Cubit community. I really appreciate that. So again, we'll have the next webinar at the same time in a week, and we'll look forward to seeing each of you there.